So, in this session we will be discussing about the non-ideal reactors. Now, this is the non-ideality is we should start tracking the non-ideality of a reactor from a special type of experiment called residence time distribution experiment. So, before we go for the detailed understanding and formalisms of RTD, we must know that what are the sources of non-ideality in a reactor. Think that we have defined two ideal flow reactors. One is CSTR, that is a continuous start tank reactor. Another is a PFR, plug flow reactor. This continuous start tank reactor, what happens? We have, it is perfectly mixes the reactant and the product, right. So, if it is Ca0 and here it is CAF, so at this very entry point we will have the concentration CAF. Everywhere inside we will have the same concentration as that of the outlet, right. So, it is this reactor, here all the reactant elements, reactant packets rather, are perfectly mixed. Right. Whereas in case of PFR, this is Ca0, now Ca is a function of Z, and finally at the outlet we will have CAF. So, Z equal to 0 here at the inlet and L here at the outlet. We have perfect radial mixing and no axial mixing. Now, you see that we have here a perfect radial mixing and no axial mixing. So, there is a specific type of idealization it generates, and here it is the concentration only changes along the direction of this flow. Now, real reactor. So, we have non-ideality creeping in. So, what are the non-idealities? Right. So, here you think of a tank reactor and we have a stirrer which is definitely high speed, but it is not perfectly mixing the contents. We have Ca0, we have Fa0, here we have Ca, or maybe here we have CAF, outflow. Now, think that from here, let us say this is pathway 1, okay. A reactant packet enters here, it moves like this and goes out. Now, over this region, as these are the region of edge or the corners, we have dead zones. These are practically, from a hydrodynamic perspective, they are separated from the rest. Now, if we have a packet moving here, so this is pathway 2. And additionally, we can think of another pathway of the reactant, which is simply like this. So this is pathway 3. Right? So the residence time of packets following pathways 1, 2 and 3 are completely different. Right? There is a complete difference of their residence time. We can understand a bit qualitatively that residence time of 3 will be the least, 1 will be the intermediate and 2 will be the maximum. So T3 is much less than T2, which is also much less than T1. Oh sorry, this is 1, this is 2. So the point what we have to note that all the reacted packets, they are not having the same residence time and they are not perfectly well mixed, because the interaction between, the mixing between these packets following pathway 3 and these packets following track 2, there are practically no interaction or mixing between these two packets. So obviously what we can think that there will be difference of the residence time, which actually triggers the different extent of mixing, right? Different extent of mixing, and this gives rise to what we refer as tank reactor. Now on the other hand, if you think of a tubular reactor loaded with maybe catalyst, right? And let us say over these regions we have a heavily dense packing. Over this region also we have a heavily dense packing. Now most of the packets will follow a least resistant pathway. However, some of the packets may pass through the dead zones. So this is 1, this is 2, and we can write that T1 is much smaller than T2. So we have non-idealities like channeling, like these dead zones, like short circuits. This is called a short circuiting path, that is dead zone, and here that is called the channeling, right? So because of this, we have in real life the non-ideal reactors, where the assumption of perfect mixing or assumption of no actual this mixing will not hold in case of tank reactor or in case of tubular reactor respectively. So we have to understand the root causes of deviation from ideality. Number 1, different reactant packets have different residence time in the reactor. And number 2, varied degree of mixing between different packets with different residence time. Right? So, first we have to understand that how the residence times of different packets they are distributed. Okay? The pattern of distribution and second the degree of mixing. So, if I focus on these two issues, first we will try to resolve that what is the pattern of this residence time distribution, right. So, that is why we invoke the term RTD or RTD analysis, that is residence time distribution analysis. And that is purely experimental. Because whether we have dead zones or not, whether we have channel pathways or not, or these distributions of the dead zones, that is practically impossible to understand, right, in real life. So, it is a kind of non-ideality. Non-idealities cannot be directly tracked via theory, which is purely a theory. There must be empiricity crafted in it. So, we will go by experimental approach of first we will try to understand how the residence time of the different packets is distributed for a specific reactor. So, this formalism of RTD was originally introduced by Macmillan and Weber. I think it is in 1935, but after that in 1952 what we follow today as RTD analysis, it was basically proposed by Dankwart, modified and restructured by Dankwart in 1952 around. So, today we mostly follow the Dankwart's formalism of RTD analysis. So, what is that? What we need? We need to perform the experiment, to perform the RTD experiment. A substance other than the reactant called tracer. Right. Now, what is a tracer? Tracer we must inject at the inlet of the reactor. It may be an online mode, it may be an offline mode. We can actually charge water through it, and we can inject the tracer in the stream of flowing water, or alternatively it may be an online mode where the actual reaction or the reactor is there, the reaction is taking place, but there may be some problems. Maybe the concentration is dropping, but we know the catalytic activity remaining the same. We have taken the sample catalyst from the reactor and checked it. We have got the result that it is performing fine, but still the conversion is dropping. So, we have to go for a diagnostic approach, right, and that can be done and the problem can be resolved by RTD analysis. So, in this case we have to inject the tracer at the inlet of this reactor, okay, is a stream of flowing reactant. So, what is a tracer, or what property, or what are the characteristic property of an ideal tracer? So, it is characteristics of tracer, which is basically desirable properties. Number 1, easily detectable by titration, by spectrophotometry, by conductivity analysis, etc. These are the common tracer. If I have to go for a very accurate experiment, we can use these radioisotopes as tracer, and we can go for this radiation measurement, and from there we can convert it to concentration. So, that is easily detectable. That must be a fundamental property. Next, it must have similar physical properties like density, viscosity, etc., as that of the reactants in for online mode and that of inert fluid water commonly for offline mode. Next, it must be non-reactive to tracer to the reactant as well as to water. It must be non-reactive in relation to reactants and water. Fourth, it must not get adsorbed on these packing materials or on the walls of this reactor. So, it must not adsorb, or it must not be adsorbed on the backing materials or on the internal surfaces of the reactor. So, these are the desirable properties of a tracer, and once a chemical satisfies these properties, we can use it as a tracer. Now, how to measure this RTD, right? There is measurement and what we will measure. Definitely we have to measure the concentration at the outlet, right. but how will you measure and what actually we need, and how will you represent this data of RTD analysis. So, next point is RTD, measurements of RTD. Actually, you see, I have mentioned that we have to inject the tracer. So, you see that if I have a reactor, anything, injection port, and here we must have a sampling facility where from we can detect that. So, we call it a detection port, and this is the reactor. Right. Now, how will you inject? How will you inject? That is a very important question to be resolved. Inject the tracer in the reactor. So, you have to inject it at this injection port. So, there are two modes of injection. One is pulse, inject all the reactors or all the tracers at a time, right? Or you can go for step mode. Produce a concentration step function, produce a step function, a step input of tracer concentration. So, first we will discuss about the pulse mode. So, what we do in pulse mode? You see that in pulse mode, your input say if this is C in and you have time, and say you are measuring somewhere here the concentration. What you will see? You have injected just side by, if you measure, then you will get something, a spike like this, okay? And this we will consider at time t equal to 0. Now, the question is, with this pulse, it can be represented by a normal distribution, but we will do an idealization of it. What is that? We will think a pulse as an impulse input of tracer, just like whatever we have studied as Dirac delta function. So, C in is some C naught into delta t, and this delta t is what? Dirac delta function, right? It is the Dirac delta function. So, delta t is equal to 0 for t not equal to 0 and equal to infinity for t equal to 0. We could have written it as simply delta t, but what is the problem? The problem is Dirac delta function has got a property minus infinity to plus infinity delta t dt is equal to 1. That is called unit impulse, right? So, it is unit impulse function. But here in actual case, it is not equal to 0. It is some C naught into the average span of time, right? So, the area under the curve, if it is equivalent, if this idealization is equivalent to this, we will write some C naught, or rather we will not write it as, we can write it as C naught into delta t. So, it will spike and go down, right. So, this is the typical pulse mode. So, if I am giving a pulse mode, what will be the respective output? So, definitely it is qualitative. Output of pulse mode. We will get something like this. We may get something like this, right. So, this is C, a C out. C and C out are same. So, the raw concentration data, how will you get that data? You go on measuring from time t equal to 0. Say you have got here a point, this is the concentration. Let's say there is a non-zero concentration you have detected at some T1, then you go on measuring at some T2, then T3, T4, T5, T6, T7, T8, T9, etc., etc. And again it is 0. So, if you join them by a smooth curve, you will get an outlet concentration profile. So, the concentration of the tracer definitely versus time plot measured, or concentration versus time plot obtained at the outlet of the reactor is called the C curve of RTD analysis. Remember this name. So, this is called the C curve of RTD analysis, typically the concentration curve of RTD analysis. Now, this C curve definitely it's a raw experimental output what we have received. So, this is the typical C curve of RTD analysis, which is the outcome of raw experimental data. But that is to be further processed, right, in order to generate some more workable outputs, which is a kind of secondary processed output from the raw experimental data of C curve. So, what we do? Here we have to go for an analysis. Let between t to t plus delta t, we have delta n number of a delta n moles of tracer molecules passing through the detection port. So, delta n is equal to C, which is a function of t, V naught the volume flow rate into delta t, where V naught is basically the volume flow rate. Say it is in meter cube per second, concentration is mole per meter cube, and this is in seconds. So, you get moles, right. So, now if we go for a limiting estimate, limiting condition, delta t tends to 0. So, we have dn is equal to Ct into V naught into dt. Now, we don't have to know basically what is the amount of tracer we have injected. We can calculate it from here if we integrate this n. So, the total amount of tracer injected is n0, which is 0 to infinity dn, or 0 to n0 dn, and 0 to infinity Ct into V0 into dt. Right. So, that is the total amount of tracer whatever we have injected. Now, when we are thinking of a distribution, it is basically what? It is basically we are trying to measure the probability of a particle or a tracer particle or tracer packet to have a residence time between t to t plus dt, right. So, the probability of a tracer molecule to have a residence time between t to t plus dt, or alternatively the fraction of a tracer molecules or tracer packets rather, because when we write molecule it may violate the condition, basic condition of continuum. So, fraction of tracer packets having a residence time between t to t plus dt, right, which is basically the probability that capital T, the variate, is less than t plus dt by 2, or rather t plus dt and t here. So, what is that fraction? It is equal to dn by n naught, and dn is Ct into V naught into dt, denominator is 0 to infinity Ct into V naught into dt. So, this cancels out. So, what do we get? This probability is equal to Ct divided by 0 to infinity Ct dt into dt, right. And we know that probability of a variate to have a value between x plus dx and x is equal to fx dx, right, and this fx we call the distribution function. So, here we have to identify. So, we define the Rtd distribution function or E curve as Et is equal to Ct divided by 0 to infinity Ct dt. So, you see that this is a new definition, right, and we can generate from the C curve. Here we have the C curve and we can generate the E curve. Right? And what is the difference between the C and E? E is a normalized version of the C. The shape will remain unchanged. The size or the area under the curve will change. Right? And additionally, what we can note here that properties of E curve. The first property, very important one, 0 to infinity Et dt must be equal to 1. Right. 0 to infinity et dt must be equal to 1. And second, functionally or shape wise, E and C curves are similar. Right. So, from C curve, in case of, but note it is in case of pulse input only. From C curve we generate the E curve. Now, just like in probability we think about the cumulative distribution in addition to the standard probability distribution, here also we can think about that, the cumulative RTD function. So, cumulative RTD function. That is Ft. So, here what is Ft? Ft represents the fraction of the tracer molecules or tracer packets having a residence time between 0 to t. Right. So, it is a cumulative distribution, and if you integrate it, this E from 0 to t, you will get f. So, this is the relation of f curve. So, definitely from this f curve, we have to feed the E curve, and we generate the f curve. And finally, it will be equal to 1. Right, because the 0 to infinity et dt is 1. When t goes to infinity, f must approach 1. So, properties of f curve. Number 1, f0 is 0. Number 2, f infinity equal to 1. Number 3, mostly it is of sigmoid shape. Number 4, if you have got ft, see, ft equal to 0 to infinity, 0 to t et dt, and we can get back to E curve by taking the derivative. Right. So, if you take the derivative, just like here the derivative is 0 and here the derivative is 0, same is the values here and here. So, if you take the derivative, and you will get some maximum derivative at the somewhat intermediately. So, that corresponds with this peak. So, derivative initially was 0, it goes to certain maxima and again drops to 0, and that is why E curve reaches to a maxima and again falls. Right. So, that is about the pulse tracer input. So, what we have noted? Initially, we have generated from the raw experimental data, we have measured the concentration of the tracer at the outlet, and from there we have first plotted the C curve. Now, normalizing the C curve with respect to the area under the curve, we have got the E curve. Now, integrating the E curve intermittently, we can generate the F curve, and we can get back the E curve taking upon the derivative of this F curve. So, that is the sequence of pulse tracer experiment. Now, next we will go for step tracer experiment, a step mode of tracer injection. So, next it is the step mode of tracer injection. Real step. So, what is that? Here you see in real life with 0 and it will be something like this. More or less it remains constant. C naught. So, this is C in versus T, right. Okay. So, here we will go for an idealization, that is the real. Just like we did an idealization in case of pulse tracer input, and we have replaced the actual pulse by this C naught into some this impulse function, unit impulse function called the Dirac delta function. Here we will also do the same idealization of step input. What is that? Here somewhat intermediate we will think that this is time t equal to 0, and we can generate this C in versus T as something like this. This is C naught, this is T equal to 0, right. So, that is the typical step input. Now, what we will obtain definitely, or what will be the tentative output? C versus T plot qualitative. What is the qualitative C versus T plot? Let us check. So, C versus T. Finally, it will attain the same step height C naught, but it will be delayed like this, right. This is a tentative or qualitative output. Now, you see that this is very similar, not same because it is C naught, very similar to F curve. Okay. So, we have to think that what will be the sequence, just like in pulse we have initially got the C curve, then E curve, then F curve. It was pretty simple and easy, right. But in step input the sequence changes. So, in pulse mode, the sequence of getting the RTD plots is C curve, then E curve, then F curve, right. However, it changes in case of step mode. So, what will be there? See, we have to invoke the formula, I am not deriving this, formula for convolution integral of RTD analysis. This is proved in the book of Levels field, but I am not proving it. See what it states, that C is equal to 0 to t C in t minus t prime into et prime dt prime, right, that will be the C. So, here we have obtained this from this, right, that is from C in. So, C in t minus t prime or C in t is equal to 0 for t less than 0 is equal to C naught for t greater than equal to 0, whatever we have idealized. So, C in case of step input, C out will be C0 into et prime dt prime, sorry, this is t. So, we can write this out 0 to t et prime dt prime, and by definition this is ft. So, here in step we will get first the ft curve from the C curve. So, this is naturally the C curve, right, and we have an equation that ft is equal to Ct versus C naught. So, here the input will be the C curve and the output will be what? The F curve. Ct versus, sorry, Ft versus T, it will be like this one. Nature wise F curve and C curve will be same. However, this value will be changing to 1 instead of C naught here, right. So, characteristic of F curve, nature wise same as, or shape wise same as C curve of step input, right. 2 f infinity equal to 1, f0 equal to 0, and we know that if we take the derivative of this f curve we will get the E curve. So, that is the universal formula. So, E is equal to df dt, right. So, we will simply go for evaluating the numerical derivative and we will get the outcome which is the E curve. Right. So, this is the E curve. So, in step input, try to understand that first we have generated the C curve, and C curve will be following some kind of sigmoid shape in most of the reactors, in case of most of the reactors. Now, it will finally attain the same concentration as that of the step height of this experiment, step experiment, and where the concentration is C naught. So, if I normalize the individual point values of the C curve by C naught, I will get the F curve, and finally the F infinity must satisfy 1 because it was going to C naught. Now, if we go for evaluating the derivative of this F curve, then we will get the E curve. Now, generally we do not follow this for standard RTD analysis, we do not follow this step experiment. So, what are the disadvantages of step experiment? The first one, large amount or quantity of tracer is required. Definitely you have to continuously go on injecting the tracer at the inlet of the reactor, so that is why large quantity of tracer is required in relation or in comparison to the pulse experiment where we are injecting the tracer, all the tracer at a time. So, we need a small amount of tracer there. So it is difficult to maintain a constant step height What may be the problem? You are delivering the tracer by means of a peristaltic pump maybe, right? And there may be malfunctioning in the pump, there may be the pump voltage in the motor coil may have certain fluctuations, right? And because of that the pump rotational speed will change and the delivery rate as it is proportional to the rotational speed that will change. So there may be problem in maintaining the constant step height throughout the entire duration of experiment. And third, as E is equal to df dt, the E curve may imbibe large errors or may incorporate large errors due to or because of numerical differentiation, right? So that's why we mostly stick to the pulse input, and with that pulse input we continue the RTD analysis. With that pulse input we continue this RTD analysis. And just before we stop this session, I would like to mention that how to represent this RTD data. So we can represent it in the form of this E curve, right? Finally the outcome is E curve. Note that, because the standard probability distribution is the important information about the residence time. Representation of RTD data or RTD analysis. Representation of RTD data, right? So conventionally we supply the E curve. However, you see a statistical distribution, right, can be perfectly reconstructed if you know the type and if you know some of its parameters. Just like normal distribution can be reconstructed, that if I am provided with the mean and the standard deviation. So two moments, one is the central tendency, the first moment, another is the standard deviation which is related to the second moment. Now we can have different types of this RTD because it is finally an experimental outcome. But investigating the large amount of RTD data for different type of reactors, finally it was proposed that if I supply the mean residence time, the variance or the standard deviation, and in addition to that the skewness, the information of three parameters is equivalent to this E curve. Upon investigating large number of RTD data sets, it was finally confirmed that the E curve information is equivalent to the specification of specification of the following parameters. right? What are the parameters? First is the mean residence time. First moment about 0. So, Tm is 0 to infinity t into et dt. Standard deviation. Right, the second moment. So, this is the first moment about origin. So, this is the second moment about the mean. It is not exactly the second moment exactly is the variance. It is a square root of this second moment. So, sigma square is 0 to infinity t minus Tm whole square et dt. And lastly, it is the skewness. S that is related to the third moment. And how it is defined? S cube equal to 1 divided by sigma to the power 3 by 2 t minus Tm whole cube et dt. So, if we specify Tm, sigma and S, it is equivalent to the supplying of E curve, right. So, that is all about today. In the next class, we will be discussing the RTD of ideal reactors and non-ideal reactors, and finally the mixing models. Thank you.